Log on, tune in, find out. Another good idea from Cambridge.
Without further ado, over to you, Peter.
Thank you. Start off by saying on the microphone.
Make sure the red light's shone on. From the top.
Is that better? Start by saying that on the programme I'm down as being the National Oceanography Centre, Liverpool, which was a shock to a lot of people, including me. The National Oceanography Centre has two branches, one in Liverpool and one in Southampton. As far as I know, I'm still in the one in Southampton. So, okay, I'm going to talk about designs for validating emulators that we use for analysing computer experiments. So, if we're going to analyse a computer experiment, and we've seen some examples already today, so we've got some expensive deterministic simulator. I'm only going to talk about deterministic simulators. So we'd run a designed experiment, and in Dave Higdon's talk he showed the design he was using, which is a space-filling design. I'll come back to that. And then we'd build an emulator using that design, and then we have to validate that emulator. We have to check that we've got a good emulator. We don't want to use an emulator. It's very easy to build bad emulators. It's quite hard to build good emulators, but it's very easy to build bad ones. So you want to check that you've got a good emulator. You want to validate the emulator. And once you've done that, then you can actually perform some inference. So I'm going to talk about design in this stage here, whereas most people actually talk about design in this stage here. Okay, so how would we validate our emulator? Well, the sort of traditional way, and Dave Higdon talked about this, is cross-validation, where we would drop one point out from our initial experiment, then we predict that point and see how well we do. We rebuild the emulator missing that point out. That's okay. I have some problems with that. One of the problems is that we build this wonderful space-filling design, and then we build emulators dropping one point out. So by definition, we haven't got a space-filling design for our validation experiment. We have it once we validate it. So cross-validation is possible, but it has some problems. An alternative put forward by Leo Bastos and Antonio Hagen is to use some validation measures based on regression diagnostics, but they take into account the correlation because we're fitting a Gaussian process rather than a straight regression. This requires a dedicated validation experiment. So you do a second experiment after the first one to use those points which are completely independent of the first experiment to actually produce the validation. And I'm going to talk about how you would build a validation experiment. So the current practice, if you're doing this, is we have an initial experiment, and I think everyone uses space filling, either maximin Latin hypercubes or Sobol sequences, or something similar to that. There are variations. And then for the validation experiment, there are a number of things people do. You can have another space-filling design. You might have a Latin hypercube as your initial design, and my second experiment will just be another Latin hypercube. I'll ignore the first design completely and just build another Latin hypercube or another Sobol sequence. Something that my group's done, and I've never really understood why we got into this habit, was if we had a Latin hypercube, we'd do a Sobol sequence for the validation experiment, or vice versa. And I think it was, I don't know why we started doing that, but we've done that quite a bit. Or if you've done a Sobol sequence, you could extend the Sobol sequence to get some extra points. But in terms of the validation of the why we're doing it for validation, there's little justification for any of those. We're really just doing another space filling design and hoping it will actually supply the validation information. Whoops. So what would we want if we had a dedicated validation experiment? What would we actually want it to look like? Well, we would want it to fill space. We'd want a space filling design because we want to validate as far as we can. We wanted to validate everywhere. So we do want a space filling design. But particularly, we want to validate where our training set hasn't been. If there are any holes in our design, we really want to check that our emulator works there. So we want it space filling, but we'd also like to fill any holes in space where we haven't been before. We also want to validate all the Gaussian process parameters, and that includes the length scales, the smoothness parameters. So we don't just want to validate a long way away from our initial points. We'd like to validate at all distances. So we want some points that are close to our original training set and some points that are a long way away. So we want to try and get all the distances so we can actually validate all the parameters, not just the mean parameters, which the filling space tends to do, but also these length scale parameters. So we need to have points close and far away. So we'd like to get this various distances. It should be all distances from the training points. So how might we design an experiment to do that? I'm going to put forward some suggestions. I don't have a criterion that satisfies all these that I can say it's optimal if it does this. So I'm going to just give some. We'll keep it again. That doesn't work. Now, we want to fill space. That was our first criterion. So since we want to validate everywhere, I'm going to insist that all the designs I consider are space filling designs. So in particular, every design I consider is going to be a maximin Latin hypercube. So that should guarantee that we have some filling of space. So my initial experiment, it's only on this slide, I'm going to call the points in the initial training experiment X and the validation experiment, which I haven't defined yet, Y. And I'm going to set up the distances, which I'm going to use to define the design. And di are going to be the distances, all the distances between x and y. So the distance from each point of y to all the x's, and then the next point of y to all the x's. And we're going to define di such those are all positive. So they're just Euclidean distances between all the points. So now let's think how we might define some criteria to define an experiment. Well, we might want to push the validation points as far away as possible from the training points. So if this is my initial Latin hypercube, I might put points down, and those are all the distances. If I maximize the sum of those distances, I'm pushing the points as far away as I can from the initial design. Okay? Then the second one is I might want to fill the holes. If I've got a hole here in my initial experiment, then to fill holes, I might want to maximize the minimum distance between these, a maximin rather like our initial Latin hypercube design. And if we're more interested in the distance between getting the uniform distribution of these distances to get these spatial scales right, then I might want to look at the Kolmogorov-Smirnov distance between these distances and a uniform distribution, so I'm sampling all the distances and try to minimize that to get as near as possible as I can a uniform set of distances. So I'm going to look at these three criteria and see, well, to generate the sort of designs I get and look at them. I say I don't actually have a criterion to say when I've got an optimum validation experiment yet, and if anyone's got any ideas, I'd be interested to hear. So initially I'm going to just produce some 2D examples so you can have a look and see what they look like. So I'm going to generate my training experiment is going to be a Maximin Latin hypercube, and I'm going to choose the best from 1,000, and then I'm going to generate 3 possible designs: the maximum of the sum, the maximum minimum distance, and the minimum Kolmogorov-Smirnov distance. And each of these are derived from 1,000 possible designs, and each design is itself the Maximin Latin hypercube from 1,000 Latin hypercubes. So you actually do generate 1,000,000 Latin hypercubes to do each one. It does take a little bit of time. This one doesn't take too much. The next experiment I show takes, well, it took 13 hours on this computer. Here's my initial experiment. Now, if I was doing this for real, I'd probably reject this and do another one because it's got quite a nasty hole up here, but that's actually quite good for my purpose because we can see whether we actually fill that hole with the validation experiments. So this is the maximum sum experiment. So the circles are the original Latin hypercube and the crosses are the maximum sum, and it's nicely filled this hole up here. And there are some close points and some more distance points. This is the Maximin design, which was designed to fill holes, and you can see it's filled this hole up here quite nicely, and it's put a lot of points in this other hole in the middle, not quite so well down here, but it has got some points that are close, and that's because the points aren't put down independently. It can't put this point, it's not maximizing the minimum distance of each point independently. They're already locked into a Maximin Latin hypercube, so it doesn't have the ability to actually push all the points out here, which would have if it wasn't locked into that Latin hypercube. And then the third one is the minimum Kolmogorov-Smirnov distance, and it doesn't fill the hole. Now, initially I thought, well, that doesn't look right because it wants to get some long distances, but of course it counts all the distances, and actually it's very easy to get long distances. It's quite hard to get short distances because when you put a point here that's very close to here, it's a long way from this point, so it's getting those long distances as well. So there's no reason for it to actually put anything into the holes. So let's just look at the histograms of distance because we wanted this to be nice and flat. So the scales along here aren't quite the same, but it doesn't really matter because we're only going to look to see how uniform this is. Surprisingly, the one that looks the most uniform, well, to me, is the Maximin one rather than the minimum Kolmogorov-Smirnov. And I think that's because I'm discounting these tails at the end, which are making the statistic bad, but we're still getting a fairly uniform distribution. This one's a bit peaky. But that's only one example. So let's just look at how each criterion is satisfied by the other experiments. So these are the 3 criteria I've got, and these are the 3 criteria they've maximized. So the maximum sum is 86, and the maximum has a sum of 81, and the minimum Komogura-Smirnov has 79. And here in the bottom table, I've just ranked them in terms of the criteria. So not surprisingly, you get 1s on the leading diagonal. Each one satisfies its own optimal criterion. The maxi-min design always comes second. So that's only one example. So let's do another test. This time we'll do something a bit more realistic. So I've gone up to 5 dimensions. I'm going to do 50 training points and 10 validation points, but I've had to drop the number of samples per Latin hypercube from 1,000 to 100 just for computational speed, because I did this on Friday, and it took 13 hours. If I'd added 1,000, it would probably still be running. But it was only running on that little laptop. It wasn't running on anything serious. So here are the same table, and in brackets I've got 1 standard deviation across my 100 repeats. Because I repeated this 100 times, which is why it took so long. So this is the standard deviation across those 100 repeats, and this small, there doesn't seem to be a lot of variation across different draws of Latin hypercubes. And if you look at the rank table again, I get the same result as I did in the 2D answer. So it looks, well, I say I don't have a standard criterion to say this is a great validation experiment, apart from the fact that I would like it to satisfy pretty much these 3 criteria here. The one that's doing we've put up a number of possible validation designs. The maxi-min criteria appears to be, well, best not the right word, I think, is the least bad, or the one that seems to satisfy my criteria in a better way. So far, I've only considered Latin hypercube designs. I haven't looked at what happens if you have quasi-Monte Carlo Sobol sequence type designs, where often people just continue to fill in the Sobol sequence to see what happens as you go higher. And I say, since I was doing this on end of last week, I've not actually seen how well they work in practice. And again, it's difficult. Well, I found it difficult to think of what's the criterion I would use in practice. Should I look for a design that makes it easy to validate or makes it hard to validate? I think I probably want one that makes it hard to validate. We want to be tough on these things rather than easy, but I haven't got a general criterion. So, anyone got any questions?
Oh, lots of questions.
Yeah, actually I have 2 questions.
Oh, okay.
2 unrelated questions. One question is generated by this conclusion. I can imagine that once you fit a Krieger model, that you conclude that there are certain areas which are much harder to predict than other areas. So there are simple parts, sub-areas. In the simple sub-areas, I would not put so many validation experiments. It's my intuition. That's my first question.
Okay, we could, yes. I haven't used the emulator to try and help me build the validation experiment. I could do that.
That's what I mean.
That might be one way to. But if there's something seriously wrong with the emulator, it might be that it says it's doing a really good job over here and it isn't. So I really do want some points to test it everywhere rather than, I mean, yes, you
You
could.
could do that sequentially, probably. So after at one validation point, you would re-estimate the Kriging model.
Yeah, that assumes the Kriging model is fairly good. If it's really bad and it's overconfident in one area region, we do need to test it there. But yes, that's another approach.
My second question, if you allow, is so you come up with how do I design my validation set?
Yeah.
I would maybe turn it around a little bit. Is when you know that after the first set there will be a validation set, shouldn't you take that into account when selecting your first set? You know there's going to be a second set.
Yeah, that's again.
So the nested design.
I mean, because in the end, once we validated it, we will fold in those validation points to build it. So we possibly should. I mean, I've built this conditional on the first set rather than building them jointly, and I probably should. Yes, building them jointly might be more sensible. Yeah.
Next
Okay.
year.
Good point.
Okay, so I'm going to go with the theme of saying two things, but I won't ask any questions. So one of the things, when you put up your simulation where you had 50 points and then 10, one of the things that occurred to me is how you might validate that is actually just run 60 points. But if you're going to do cross-validation, what you might do is take space-filling designs of 10 points within the convex hull of the design, right? So you probably wouldn't eliminate the boundary points, but you might actually do cross-validation with removing 10 points from the interior, but remove them using a space-filling criterion rather than just moving them at random. That might be an idea. The other thing that you might consider doing, since what you wanted to do was having space-filling, but you also wanted to look at these different length scales, was, so just to add another word to the vernacular, is use a cascading Latin hypercube design, where these things are, you get a Latin hypercube design, but you also have clusters of points around, like you have little clusters of the whole design is a Latin hypercube design, but you have clusters in different areas, and that way you get the different length scales. Those might actually be helpful in that case.
Another criteria which in higher dimensions may become important is that of looking at the projections of these points into various subspaces of 5D. I mean, it may not be just good enough to have points that maximize a minimum inner point distance in 5D, but you'd also want to know that, particularly if not every variable is active in this, that should only 3 of the 5 be active, that when looked at in the 3D space, that's also space filling. So I think the criteria itself might be tweakable to look at a different kind of minimization overall to, let's say, some dimensional projections.
Yeah, I think that's true. I think in practice, I can see there's two ways you might do this. One, you might do all the runs at the same time, in which case you can't use the emulator to help design the second batch. Sometimes that happens because we're given there's 20 workstations, you can run 20 jobs. We have to do both at the same time. If you can do it sequentially, I think yes, you learning from either by finding where the emulator says it's not going to do good, though I'd say you do have to be careful that you validate where it may be overconfident. But also, yes, if we could remove some of the variables, then we could actually validate in a smaller subset. But again, you still want to test that that's a correct answer, that you just haven't missed something in that initial design. To validate properly, you want to validate everything that's coming out of there, including
you have to take into account both projections as well as in 5D plus 4D plus 3D or whatever it happens to be.
So you spent a lot of time starting from scratch on getting these various criteria met. And I was wondering if maybe spending that much time doing an evolutionary design that sort of did switches but would have criteria that say, well, you can't do this switch because you mess up this criteria, or you do this switch, it helps. So an exchange algorithm, as opposed to starting from scratch, having these designs sort of evolve and let the exchanges be controlled by the 3 different criteria. You might get different kinds of designs than what you did there.
I noticed in your first example, The first design had a great swathe of points going down a line, and two of your good designs had a similar pattern. And so yeah, you see there?
Yeah.
And I'm just wondering if your criteria are forcing the second design to be in some way rather similar to the first design, even though the points have been moved, and whether that might be a problem.
I think.
Or is it just happen in 2 dimensions?
No, I think my criteria are in this case, it's forcing points into the holes.
Yeah. But that means if
they're
they've got
constrained,
like that,
they're constraints, but that is going to have a better minimum distance than one which has got some points
over there.
closer there. This one doesn't do it so badly.
True.
So there may be some factors, if we looked deeper into these maximum, which is the one that comes out best, which have some unfortunate properties that we would want to investigate further.
Question there. For your KS test, what is the distribution that you're using for comparing?
Uniform.
Uniform. Because if I pick 2 uniformly distributed points on the square.
Yeah, I haven't taken any account of the corners.
Yeah, so maybe that might be
yeah.
one of the performance problems.
Yeah, that was just too, it was too hard for me.
It might be because it was done this Friday, you can't answer the question, but what happens if your validation states that your emulator isn't very good and you therefore want to improve your emulator? Is there anything you need to be careful of by improving it with the points that you've just picked? Because you haven't come up, in cross-validation, you come up with a design that's all okay and I can just use them. But if I've got a whole bunch of new points that I didn't think about when I did my first design, am I going to overfit anywhere by adding those points in? Or do I need to worry about anything?
I think what you mustn't do is just fold the points in and say, now I'm going to build something and then I've got nothing left to emulate with. If you keep holding those points back and say change the space scales, and you rigorously don't use the information from the new points to help get those space scales, you're probably okay. But you do have to have a sort of self-denying audience say, I'm not going to use any information from the validation to do that. Or you have to do yet a third experiment to do further validation. I think you mustn't, you've got to be careful not to use the same information twice when you rebuild the emulator. That's very important.
This is just a follow-up to that. There was a recent paper by Moore, Loepke, and Williams. They call it emulator maturity, where they do something like what you're doing, starting with a space-filling design, then add more points. But the point is to not just to do validation, but to improve the predictor if the first predictor isn't very mature, doesn't fit well. And so they actually do something like what you're doing, Peter, and in their tests, that turns out to work fairly well.
Okay. Yeah, I mean, I haven't looked at that aspect.
That's right.
But you could, dual use would be another thing where you would try and reduce the sort of mean square error or something at the same time as testing it. That would be an interesting.
So that's in the Journal of Statistical Planning and Inference. It's a fairly recent paper that talks about that issue.
I'll take this opportunity because we still have a couple of minutes left to make a comment which sort of picks up on Jack Kleinen's one about shouldn't you be designing like this from the beginning. If it matters, if you're worried about getting the length scales right and you need some points close to check that, should you not have had some points close together in the original design in order to get the length scales right in the first place?
Yeah, well, I believe that.
Yeah.
Well, I've worked on designs like that, but in general, that's not what people do.
No, I know.
Because it's quite hard.
Well, so just to clarify, we have to be a bit careful because if you're going to fit separable covariance functions, then you've got a correlation length for each input, and therefore, in the projections, they are close. It's only in the p-dimensional space that they may not be close.
Right. Yes, yeah, fair point.
Sorry, my watch is a bit fast. That's why I stopped.
All right. Okay.
You said you didn't know which was your best criterion.
Yeah.
And it's probably a bit more of an annoying comment. You might decide to combine, you presumably use some kind of evolution research to get your maximum designs. Maybe a multi-objective search would allow you to look at the trade-off between one criteria and another. And you might find that actually if they weren't so in tension with each other.
Yeah, but I don't do anything as sophisticated as evolutionary research. I just generate 1,000 and take the best.
Okay.
So it's very, there's nothing, say, there's nothing clever to play with there, but it might be we should do something a bit
The actual
better.
question though was,
Yeah.
one thing I don't get was where you're trying to get the different length scales.
Yeah.
Why in your criterion did you take the distance to all points and not the minimum distance? Because say you're trying to maximise the distance between from one point, get a range of distances between points. Well, there could be one point in between the distance you're calculating. I don't see why you don't take the minimum distance from one point to the next point and then rank those and use that as the criterion rather than the distance to all points. If you can unbubble what I've said from all the repetitions of the word points.
Well, I think because when I do, if I predict what's happening here, then the distances to all points matter.
Is it not just the distance to the nearest point? Is that not more informative?
The nearer points have more.
The nearest have more effect, but they all have it depends a bit on the correlation, the form of the correlation function you're using. In a sense, I've been deliberately naive here and not used any information on that. I mean, if you had you could have a limited distance, in which case it would matter. Whereas if you're using something like a Gaussian correlation function, which is the one we use most often, it probably is using all of these. Because it doesn't tilt
it would maybe give you a more useful criteria because you've got all these overlapping distances. It's going to be less useful to differentiate between designs if you have distance to all points. So it's almost like overlapping gear ratios on a bicycle, in a way.
Yeah, I do see the point.
Okay, I think we have to. You've had so many questions. Thank you very much, Peter.